Good morning. So we go to the next chapter, which is actually a very important one. Today I want to talk a little bit about the ideas behind the notion of complex numbers. So mainly I want to motivate you because this is a little bit mysterious to the students in the beginning. Let us try to do my best to motivate why this is an important topic, okay? So the idea of the complex numbers started actually by called Friedrich Gauss, which is called the Prince of Mathematics usually. And then he was concerned about solving polynomial equations. Okay, so for example, polynomial equation is an equation in which you have a polynomial equals to 0. Okay, and then, for example, if I give you a very simple one, x minus 1 equals to 0, if I ask you to solve that, it is a polynomial of degree 1 equals to 0. So if I ask you to solve that, x becomes equal to 1. And then we had a set of numbers, the set of natural numbers, say for example, starting from 1, 2, 3, 4, etc. So this set was enough to solve this equation. It was also enough to solve that equation. I don't know. Because if I solve that equation, I get an answer which belongs to the set N. Yes? But then you immediately realize that this set is not enough for solving all possible polynomial equations. For example, if I just change this to x plus 1 equals to 0, then the answer is x equals to minus 1, which of course does not belong to N. So it motivated somehow mathematicians to extend the set of natural numbers to a bigger set. And the set is the set of integers, which contains also the negative ones and 0 as well. So for example, we have minus 2, minus 1, 0, 1, 2, and etc. Then this set is of course enough to solve this one and also that one. Yes, because the roots of these equations belong to set C. But immediately you can guess another polynomial equation whose root is not in this set. Let us make it very simple. So for example, 2x minus 1 equals to 0. If you want to solve that equation, then what happens? X becomes 1/2. And 1/2 does not belong to this set. Again, mathematicians extended this set. What is the set called? Do you remember? It's called the set of rational numbers, which is the simple. This Q comes for quotient, and this natural, of course, N. And this is from a German word, I think Zahlen or whatever, meaning number. So that's why they use Z there. And this is Q for quotient. So this means that this is the set of all fractions such that the numerator and the denominator are coming from the set of integers, but of course with an extra condition that the denominator is non-zero. But again, this is not enough. Yes? For example, I can assume that x to the power of 3 minus 5 is equal to 0. If I ask you to solve that equation, then what happens? X becomes the third root of 5, and it can be shown using rigorous mathematics that this number is not rational. This is the set of rational numbers. This number is not rational, so it does not belong to this one. It is not possible to find two integers so that when you divide them, it becomes exactly the third root of 5. So this is not rational. So this means that mathematicians actually had to try to expand this set even more, and this is why they come up with the idea of the set of real numbers, which is, by the set theory language, is the union of Q with irrational numbers. In the language of set theory, irrational numbers are the complement of the irrational numbers. The set of irrational numbers is the complement of the rational numbers if the universal set is a set of real numbers. But I don't want to distract you with that, so we extended that one. So what is happening? So if you consider the Venn diagram let us consider that this is the set N. Then we extend this set N to set Z, which contains that one. You remember what is the set theoretic language for this? We say that N is what for Z?
A subset of.
It's a subset, yes? And then I make it bigger. It is Q. Do you agree with me that Q contains Z? Why Q contains Z? For example, why do you think 5, which is a number in Z, is also a number in Q? Yes?
You can write it as 5 over 1.
5 over 1, yes, exactly. So this Q also contains Z, and then R contains all of them, yes? So this is R. If you want to imagine, it's good to have this imagination. So, every natural number is an integer. So natural number, the set of natural numbers is a set of the integers. This is the subset of Q, and this one is also a subset of R. Of course, the set of irrational numbers, you don't see it in this diagram, but can you show me where it is I is? Where this I? Where is this I? Yes, Aaron?
It's everything that isn't Q.
Yeah, it is this rim, yes? So it is outside Q, but inside R. So that is I. That's also a subset of R. Okay, but this is not also enough. So Gauss was thinking about this problem. So what happens if I want to solve a simple equation? X squared plus 1 equals to 0. Okay? Then you see that you should give up if you do not want to extend your sets to a bigger one. Because can we solve this in R? The answer is no, because if I want to solve this means that I need to find a number whose square is equal to -1, and we know that this cannot happen if I choose a real number for x. Because if x is 0, x squared is also 0, which is not working. If x is positive or negative, it doesn't matter. Its square turns out to be positive, so it cannot be equal to -1. So that was a starting point of this idea of complex numbers in the brain of Gauss. And he was thinking that is it possible to find a number, to set a new system of numbers which contains the solution of this one. Of course, if you want to do that, you need to imagine things, yes? And this is sometimes they call imaginary numbers, this set of complex numbers. So he said to himself that let us assume that there is a number, but of course not in this set, that its square is -1. And let me just call it I for imaginary. Let us imagine a number whose squared is -1. Okay? Or in a better way, let us assume that this I is a square root of -1. So you know that square root of -1 in the real numbers is not defined, yes? So let us imagine, that this is the word that I'm using. Let us imagine there is a number in a bigger set whose square is -1, okay? And then let us explore the consequences of this new rule of the game to the algebra that we already have. Yes, and then if you're a mathematician, it is better. So you have some algebra, you know some algebra, you know how to add numbers in R, to divide them, raise them to powers, whatever you did with real numbers. Let us keep all those rules intact, but let us add a new rule to the game. That there is a symbol, there is a number, whose square is -1, and try to explore the consequences of this innocent assumption. Yes, that's what I see. But if we can imagine that, then there is an answer to this one. What is the answer to this equation then? X squared is -1. I. But if you ask me what I is, I don't know. I'm just imagining what I is. By the way, it's not very strange. If I ask you what is the square root of 2, square root of 2 seems very plausible and natural for you. But if I ask you what's square root of 2, what do you answer? No, that is an approximation of square root of 2. So it doesn't matter how many decimal numbers you present, that is not really square root of 2. It's a good representative of a square root of 2. But what is the meaning of a square root of 2 in mathematics? Yes, Dan?
It is a number, so that when it's squared, the answer is 2.
Is 2. It's exactly the same story, yes? But there is more to it. A mathematician has already shown that there is a real number whose squared is exactly 2, which we don't study in high school. And then that number is unique if it is a positive. Then that number is called the square root of 2 and is symbolized by this symbol that you know. So if now more or less in the same spirit, if I ask you what I is, you see that more or less it's the same thing, exactly. I is a number whose square is -1. Yes? But of course it is weird because we do not have that number. I just want to demystify, how do you say that, this mysterious things on imaginary numbers. I just want you to know that we are making a new game. That there are two problems. Is this game a useful game? Might be it's an interesting game. For example, chess is a very interesting game, but is it useful or not? Probably not that useful. Okay, but then this of course is useful for people who are earning money from it or whatever, and make you entertained. But that's good. But I squared equals to 1 -1. That is a very nice story. So it was in around, I think, yes, I think 19th century. Yes. So he was just thinking about this problem. Okay, and so this is the idea. This is the logic behind your head. So I want to keep the algebra of the set of real numbers intact. I want to add a new rule to the game. And by the way, it's very natural. You can, in principle, destroy everything you have constructed so far, but that's not a good idea. So let us keep every algebraic properties the same, but I want to add one rule to the game. And that's I squared equals to -1, and I want to explore these consequences. Okay. But that's also good, interesting to see. It seems a little bit more than that. Let us try to connect it with this 20th century physics. So, for example, you know that classical mechanics, invented mainly by Newton, or discovered by Newton, was very good in designing airplanes, constructing buildings, bridges, and everything. So you calculate things. For example, if you want to design a bridge, you can calculate things, and then start doing the bridge. But then, in the beginning of the 20th century, physicists probably thought that it is not a good idea to be a physicist because physics has come to an end. We discovered everything we want to, so there is nothing to discover, so let us have a different occupation or career. So then something strange happened. When the technology advanced a little bit, they tried to apply Newton's laws and, of course, Maxwell's laws in electrodynamics to predict the behavior of electrons, subatomic particles, yes? And then it was starting a little bit of strange things. You might have studied a little bit of it in physics. For example, using Newton's mechanics, you can throw a ball. Okay, if you know the initial velocity of the ball and the direction of the projection and the force that you kick the ball with, then you can predict at this time the ball would be at this point. And then when you predict this on paper and then do the experiment, they match very good. Okay? But they wanted to do some kind of these kind of experiments for electrons, which were they thinking that also they are balls, but much tinier balls. But then when they predicted that, the deviation was very, very large. So when they used Newtonian mechanics to calculate that, and then they do some experiments to test the idea of the prediction, they deviate a lot, okay? So then they say that, okay, there is something wrong, okay? Of course, in the beginning, they want to fine-tune Newtonian mechanics so that it fits, but eventually they gave up, they realized that this is not working, and then something interesting happens. So there is another equation in quantum mechanics that predicting the behavior of an electron, which is not Newtonian mechanics. So if you have Newtonian mechanics, you have force equals to the mass times A. For example, this is the mass exerted on an electron, that is the mass of an electron, and that is the acceleration of the electron. If you write it in the derivative language, So you can see that m is the mass and a is this acceleration. So you can write it as the second derivative of the position with respect to time is equal to the force. So that is the Newton's formula. Okay, so if you apply this Newton's formula for electron, you do not get the correct answer. Then another person who is called Schrödinger, Austrian physicist, he wrote another equation for electrons. And the equation, let me just write the equation. It's a little bit complicated, but don't get involved with the equation itself, okay? Okay, something like that. So you really don't need to know anything about this equation. So this is somehow a fancy derivative. It's called a partial derivative. This is time, that is a position of the electron, and that is the potential energy. And this psi is called the wave function. It's a little bit mysterious. Let us not go into it that much. Okay. And then this is very interesting. For example, assume that Schrödinger wrote this equation for you, and then using this, you try to predict the behavior of the electron, still it does not work. But strangely enough, if you put an eye, who Gauss actually invented 100 years back, more or less, it starts working. Okay, so then I don't know. So what do you think? Is eye real or imaginary? Because electron apparently is something real in our universe. And then if you don't put I, what you predict is wrong. But when you put this imaginary number there, suddenly everything is predictable in a correct way. Okay, so that is, I don't know, that's up to you. From philosophical point of view, do you want to consider this an imaginary number or a real number? Because it's predicting something real. But one thing is different. It is not possible to measure something and the answer is a complex number. That is for sure. So for example, I cannot measure the momentum of an electron and the answer turns out to be a complex number. So the numbers in measurements are always real numbers. Okay? But if this I is crucial there, if the I is not there, the predictions are all totally failing. But if the I is there, which was not even in the mind of that, even the prince of mathematics, that what he's inventing will be somehow useful in physics, yes?
What if the partial derivative is imaginary? How do you know it's not?
No, partial derivative, if you want to understand it, you need to understand it from calculus point of view. But it doesn't have imaginary numbers there.
Because I was thinking if you have two imaginary numbers and they're connected, it becomes one real.
No, not in every situation. They have to be conjugate of each other and then if you multiply. But anyway, I just want you to understand, of course you are right, the psi itself is imaginary. Yes? But even psi is imaginary, it means the complex numbers is integrated in this equation. And without imagining that this is imaginary, the predictions are wrong. But when you imagine these numbers to be in the set of complex numbers rather than real numbers, the predictions that you get out of them are real, are working. That's what my point. So I mean, in physics, when he was inventing this, he was solving a pure mathematical problem. It has nothing to do with physics. He was looking for ideas to be able to solve all polynomial equations. But in this case, later people use this idea, which is a really totally different setup, and then we were able to finally predict what is going on. But of course, still quantum mechanics is so mysterious. People use it to calculate things, but people believe that they don't understand it. Okay, so there are very bizarre consequences of what quantum mechanics predicts. But it is working because you're using your iPhone, computers, and everything is working, okay? So let us now forget about that. So this is some kind of motivating introduction to this one. And don't resist about what I is. If you ask me what I Babak is, I don't know. I would say that I is the square root of -1. But if you insist what is the square root of -1, I cannot answer you. I'm just thinking, I want you to think in this way. We have the set of R. We know some algebra on R. We want to keep all the algebra we want to add one new rule to the game, and we want to explore the consequences. Okay, now from mathematical point of view, defining it is easy. So I would say that when I say a complex number, so this is my definition, a complex number z, usually these are the letters Z and W are the standard letters that you use for complex numbers. So I say Z is a complex number if it can be written as A plus B times that I. So a complex number is a number of this form where A and B are real numbers, A and B belong to the set of R, and I is a square root of -1, with the property that if you square it, it gives you -1. Okay? This is just, assume that we are inventing a game. But it really turns out to be a very, very useful game, not in only in the realm of mathematics, but in the realm of physics as well. Okay, which was not even predictable for the founder of this. Okay, so if I ask you what is a complex number, this is something like this. These two numbers should be real. For example, 5 plus 3i is called a complex number. Yes? And then there are some names. This number without I is called the real part of z. And there is a symbol for that even in the book. So you write RE for real, and then you put a Z here inside. So R real of Z is just what? A. And then this number B, be careful, the number B itself is real. That B part is called the imaginary part, and it's denoted by IM for imaginary of Z is B. So, real and imaginary part of the complex number are both real. So if I ask you, for example, if I give the name W to this number, if I ask you what is the real of W, the answer is 5. And if I ask you what is the imaginary of W, don't say 3i, you should say just 3. This is definition, okay? If the real part is 0, if the real part of a complex number is 0, we say that Z is called a pure imaginary. A pure imaginary number. So let me write it. If real, this is 0, then Z is called a pure imaginary number. And then, by the way, there is also a name for this famous I. This is called the imaginary unit. So this assumption, the one thing I want you to understand, even though it also appears in physics, but I told you that if you measure quantity, the result should be a real number. So the thing that we need to talk about, the way that we have to think about the set of complex numbers is we use this idea, but finally we want to explore something about the set of real numbers. Okay? And it turns out that this is a very useful tool. For example, you have some familiarity with the notion of integrals. So there are many integrals that we cannot solve directly, but we can use the ideas in the complex analysis to solve them. Okay? So this means that we change the problem given to us in the form of an integral. We use the theorems in this field of mathematics. We promote this integral to another integral in the set of complex number, do something there, and get some answer there. and then come back to the world of real numbers, interpret the result in the language of the real numbers. So this is the way that you need to imagine that. Another thing I want you to write, so the set of complex numbers, let me introduce it mathematically. So this is denoted by this symbol, C for complex, and that is the set consisting of all the numbers of this form, such that A and B both belong to R, and I is the square root of -1. So if someone asks you to define a set of complex numbers, this is one way of defining it. Now, let me ask you one question. Do you think this is correct or not? Intuitively and rigorously, do you think this should be intuitively correct? Do you expect this happens?
Yes.
Yes, because I told you that the goal is to extend the set of real numbers to a bigger set, so that in that set I can solve this equation. So this is this is what you imagine here. So the set of complex numbers is bigger, containing all the previous sets of numbers. So this is what you expect, but is it really true? Do you see that every real number is inside C, and if the answer is yes, why? For example, if I give you 5, 5 is real. This is for sure. The square root of 2 is real. But now let me ask you, do you think that 5 is also a complex number? Do you think the square root of 2 is also a complex number? And if yes, why? Yes, Aaron?
I'd say yes by the definition.
How, for example? How? Because the definition of a complex number should consist this symbol of I.
Because you can, for example, 5 plus 0.
0, exactly. So 5, exactly as I told you. You told me that 5, so you told me that 5 is also a quotient, is a rational number, because 5 can be viewed as 5 over 1. So here 5 can be viewed as 5 plus 0 I. Okay? And by the way, what is 0 times I? Why? Because my rule was to keep the algebra as before. So that was the rule of algebra in the set of real numbers. Every number multiplied by 0 is 0. I want to keep the algebra as before. So 0 plus I is still 0. So this is why 5 is also a complex number. So this shows that if R is a real number, you can write it as R plus 0I. Then it turns out to be a complex number as well. So this means that R belongs to C. So if I choose R in R, then R also belongs to C. So this means that R is a subset of C in this language. Okay, and then there is one more question. The question is that, is it possible to find another polynomial equation so that C is not enough to solve it? And that was the problem that Gauss was working on it. So do you remember? So do you understand that what is happening? It is natural, by the way, yes? I started constructing polynomial equations, and based on the solutions that I get, I was motivated to expand the set I am working with. And then I got this equation, and I introduce a number. Do you think that this is enough, or might be by coincidence or by clever guess, someone can come up with a polynomial equation so that C is not enough to solve it and people have to extend it even more? I just want you to feel that the problem is real. Yes? And the Gauss was working on it, and his PhD thesis, he proved that no, we don't need to go beyond that. Okay, so this is the end of the hierarchy here. This is the end of the story. So you don't need to extend C to a bigger set. Every polynomial equation, no matter what that polynomial is, has all its roots inside this set C. So that's also the end of the story. We don't need to expand. That's a relief for us, yes? So we don't need to think about extending this set indefinitely. That is enough. So I just want to pass this information for you to understand if you want to understand if you want to understand this topic a little bit deeper. Okay, so hopefully this is a good motivation. Now we want to set up an algebra on the set of complex numbers, but I told you that I want to keep all the algebra of the set R intact. I want to explore what are the new consequences of this single assumption. Okay, so if you want to construct an algebra, what do you do first? We did this algebra in set theory as well. I introduced what a set is. What was the next step immediately after introducing the sets? Yes?
So like what would it mean to add or subtract?
No, before that. Before defining operations on sets. So you are talking about union and intersection, but they are coming later a little bit. Before that, we needed to understand what is the meaning of two sets to be equal. And that's the same thing here. What is the meaning of two complex numbers to be equal? By the way, that is your choice because you want to construct this. But try to think as natural as possible. If I give you two complex numbers, how do you see that these two complex numbers are equal? Yes?
I'd say if it's the real part, then the imaginary part are
Correspondingly equal. Exactly. So that's our definition. So definition, complex numbers z equals to a plus bi and w equals to c plus di are said to be equal if, of course, and only if. When you define something, it automatically means if and only if. If and only if, what happens? The imaginary parts are the same and the real parts are the same. If and only if A is equal to C and B is equal to D. In other words, if I write A plus BI is equal to C plus DI, this happens if and only if A is equal to C and B is equal to D. This symbol means and. And by the way, this is one of the powers of complex numbers over the real numbers, because when you have equality of two real numbers, that gives you one piece of information, equality of those numbers. But if I give you the equality of two complex numbers, what do you get? You get two pieces of information, the equality of real parts and the equality of imaginary parts. So it passes you one piece of information more than the equality of two real numbers. By the way, is 0 a complex number?
Yes.
Yes, because it can be viewed as what? 0 plus 0, I. Okay, for example, the consequence of this is this. When I say A plus BI is 0, what can you conclude? According to what I told you, yes?
A is 0,
B is 0. It's important to understand. But remember, it's a little bit different. I want you to understand. If I write it in this one, in real algebra, if I say x plus y is equal to 0, are you allowed to conclude x is 0 and y is 0? No. Be careful. I want you to differentiate differences. This is coming from what I defined here. So instead of 0, you imagine 0 to be this complex number, and by that definition, you are allowed to conclude that A is equal to B is equal to 0. So that's important to know. Yes? Yes? Okay. Now, so for the time being, A and B are real. We will talk about that, what happens if A and B themselves are also complex numbers. But if I ask you what a complex number is, and by the way, this is called the standard or Cartesian form. It's called Cartesian form of the complex number, okay? Or the standard form. So when I say write this as a standard form, you have to write it as a real number plus another real number times I. Yes? Okay, so this is the first thing we do. For example, let me give you a very simple example here. Example. Determine the real numbers x and y such that, I don't know, for example, 2x minus y plus iy is equal to y minus x plus I x. Hopefully it will work. Okay, so by the way, it's important here, so let me emphasize here. Because if I don't say that x and y are real, then I cannot say this is the real part and this is the imaginary part. In order to say this is the real part and this is the imaginary part, by the way, I use them interchangeably. Sometimes I put I on the left, sometimes I put I on the right. It doesn't matter. Because I told you that I want to keep the algebra the same. Okay, so now what can I do that? If I want to solve that, I see that the left-hand side is a complex number in its standard form. Why? Because this is a real number plus another real number times I. This is also a complex number in its standard form. It's a real number plus a real number times I. So these two numbers are equal if and only if what happens, the real part of the left side matches with the real part of the right side. And the imaginary part of the left side should also match with the imaginary part of the right side. And then I get a system of equations and try to solve. That's very simple. So for example here, I get 3x is equal to 2y. And from here, I have this y is equal to x. Then if you put it there, you get one simple answer. X is equal to y is equal to 0. That's the end of the problem, okay? I want you to understand the difference of this algebra. If that is not a complex number, there is no reason that I believe this part should be equal to that part and this part should be equal to that part, unless it is in the realm of complex numbers, okay? Okay, what is the next step? So we want to start a new algebra. We introduce the concept of real complex numbers, and then we define what is the meaning of being equal, and then next, operations. So addition, subtraction, multiplication, and division. These are the four main arithmetic operations. But I can define it for you, but I want you to tell me what do you think it will be a good definition if you are a mathematician and you know the goal. The goal is to keep the algebra intact, the algebra of real numbers intact. I want to add one new rule to the game, and that is I is equal to square root of minus 1. So if I have z equals to a plus bi, and if I have w equals to c plus di, can you tell me what is a good way of defining z plus w, and what is a good way of defining z minus w? So I put a semicolon here. It means that I am not calculating it, I am defining it to be equal. Semicolon equals means defined to be equal. Defined to be equal to. So, but what is a good definition for z plus w? Yes?
A plus bi as a whole plus c plus di.
Which gives result to what? What is the natural to things? Yes, you are right. A plus bi and then c plus di. But I told you that I want to keep all the algebra the same. So what happens? It means that I can add a and c together, and between them I can factor an I out. So this becomes what? Plus b plus di. Yes? So if the algebra of the real numbers is as before, this is not strange. So this is what we get as the definition. Yes? And then, what do you think about the difference? What happens with the difference? The same thing, but with a minus sign. So minus goes in, I have A minus B, I have C minus D. A minus C, because this becomes A, this becomes minus. This also becomes minus because minus goes for both of them because the algebra is supposed to be the same. And then I take this one with that one, and I take these two and I factor an I out. It's very natural. So if you want to express this in English words, what do you say? If I want to add two complex numbers, I need to do what? I need to do what? I need to add the real parts separately, and I need to add the imaginary parts separately. If I want to subtract them, subtract the real parts and subtract the imaginary parts separately. So if I ask you what is the real part of z plus w, what's the answer?
A plus
A plus c. If I want to write it as a formula, I can say real part of z plus real part of w. And if I ask you what is the imaginary part of z plus w, it is the imaginary part of z plus the imaginary part of w. And if I ask the same question for subtraction, we will have this one. Yes? Is that understandable? If I ask you what is the real part of this number, you tell me a plus c. But what is a? A is the real part of z. What is c? Is the real part of w. That's what I have written the formula like this. So I want you to get familiar with the notations we are using. Are you feeling comfortable with what I have written here? Yes? Because if I ask you what is the real part of this number, what is your answer? If I give you this number, I ask you what is the real part. What do you say? A plus C. Yes? But now I go here. I ask you what is A for this number. You say A is real part of Z. And if I ask you what is C, you say C is the real part of W. Yes? So that's why these formulas are correct. So I don't want to give examples here because I think they are very simple, but let me just write one. For example, if I give you Z, 2 plus 5i, and then W, so minus 3 plus 2i. Okay, so if I ask you what is Z plus W, what is the answer in your head? What's the answer? Minus 1 plus 7i. Extremely simple, yes? What is Z minus W in your head again? 5 plus 3i, yes? I'm subtracting. Okay, things, yes?
Can you have negative I? Your real positive, you have an example.
Yeah, you can put negative I. Yeah. So if you want to, let me change, that's also a good question. So let me change this to negative 1. And if I add these two, what happens? It becomes minus 1, and then it becomes what? Positive 3. And then if you subtract them, it becomes 7, yes? But you can also have negative 7 at the end. It doesn't matter that much, yes? So am I right? Subtract them, it's 5, and then 7, that's correct. If I, for example, calculate the other way around, this becomes minus 5 minus 7. That's possible, yes? But things become more interesting if you want to multiply them and then divide them. Okay? So I can write a little bit of strange formulas for multiplication and division. Then I want to motivate you why these formulas are defined in this way. So I would say that, let us say that Z is A plus BI and W is C plus DI. I define Z times W is defined to be equal this AC minus BD as my real part, and then plus AD plus BC as my imaginary part. It's a little bit weird of definition, yes? So this tells you that if you want to multiply two complex numbers, take the real part of this, multiply it by the real part of that, and subtract the imaginary part of this, multiplied by the imaginary part of this, and put it as the real part. And then do this. Multiply the real part by the imaginary part, multiply the imaginary part by the real part, add them and put them as the imaginary. So it's a very, apparently a strange way of defining things. But I would say that this is the only way to define if you want to respect the algebra of the set of real numbers. The division is even more weird. So if you want to define this, I even don't remember the formula probably. Let me just do that. And then what you do is to AC plus BD here, if I'm right, and then BC minus AD. So this is also a very strange definition, yes? You might ask, who was that person who defined this division so crazy, yes? So if you want to divide Z over W, it's a very strange, yes? You take the real part of this, multiply it by the real part of that, imaginary part, and then you divide that by this squared plus that squared in the denominator and so forth. Okay, but I want you to motivate you. I want to make it very natural to you. If I want to respect the set, the algebra of real numbers. Okay, let us try to understand this. By the way, from a mathematical point of view, they are definitions, so they don't need proofs. But it's a good idea to motivate why on earth you need to think about this kind of weird definitions, yes? The product is extremely simple. I think you can motivate me immediately. Can you motivate me why that's a good definition if I want to respect the algebra of real numbers? So let us multiply them. So Z times W. Okay, A plus BI multiplied by C plus DI. Okay, so I told you that you are supposed, my goal is to respect the algebra in R. So if the algebra in R is respected, what do you do? So one of the main laws of algebra of real numbers is distributivity. So you can distribute that. So I told you, let us respect that. So what we do, we distribute. I take A, multiply it here and there. I take BI, multiply it here and there. Yes? Is it natural to you or not? If it feels natural, it means I am respecting the algebra of R. Because you already know what's the algebra R. But now, something strange happens here because that's I squared, but we know what is the property of I. You are not allowed to write I is equal to square root of 1 minus 1. Sometimes we do, but you usually need to use the letter I. Okay, so for I keep it as I, but for I squared, I can write what? Minus 1. So this I squared is nothing except minus 1, then these two parts become real. And then I combine them, so this becomes AC minus BD. And between these two, I can factor an I out. Yes? So this is, even though it was a little bit weird to define the product like that, so this is, be careful. What do you expect usually? Because when I write Z plus W is A plus C and then plus B plus DI, you might think that ZW should be A times C plus B times DI. Yes? Because you think that, okay, when I wanted to add, I added the real parts and imaginary parts separately. Why not, if I want to multiply the real parts and imaginary parts separately? If you want to do that, no one resistable, no one will be against you unless they will. Mathematicians are actually very decent people, so they listen to you what you are saying. If it is nonsense, then they start moving, leaving the session, yes? But if you think that's a good definition, you have to stand for it and then motivate people. Let us listen to me. This is a good definition. Okay, but if you define it in that way, it is in violation with the algebra in set of R. Okay, it doesn't work. You cannot have both of them. Okay, either you have to decide to sacrifice R in favor of C, or you want to keep the algebra in C. So mathematicians have defined it. Of course, you can be also your own mathematician to design this. And they explore the consequences, by the way, of that graph. Okay. Let me also motivate this one. What I want to do for z double over w, this formula is not in the formula sheet. And you are not supposed to memorize that. So you have to redo what I'm going to do here case by case. Okay, so you need to learn that. This is more or less a new thing. Okay, so what I want to do, is to motivate this formula for you. To motivate why this formula is correct. So, z over w, z is a plus bi divided by c plus di. Okay? You might say that why shouldn't we leave it like this? What's the answer? Why do you think I don't leave it like this? There are many numbers in real numbers, I leave them like the fractions, yes? If I write 1 over 3, I leave it like this. But why do you think I shouldn't leave this like this and say this is the answer? Yes?
Maybe because we can't identify the real and imaginary.
Exactly. Thank you very much. Because we want to write a complex number in the form of a standard complex number. A standard complex number is the real part plus an imaginary part. Is this number of this form yet? No. So this is why it is different from this situation. I'm not allowed to leave it like this. I have to extract the real part and the imaginary part of that fraction. But there is a standard trick, I want you to teach that. And this is interesting. You repeat the fraction and you multiply it by the conjugate of the denominator. I will tell you what the conjugate is. The conjugate is the same thing that makes a conjugate rule with the denominator. So meaning that this one. Okay? Is it natural to do it? Because I'm not proving things. I'm trying to make it plausible to you. So what is this number? Why? I want you to feel this is strange. Because if you say this is 1, it means that you know how to divide. If you already know how to divide, so what I'm teaching you. Why this is 1? Or why it is good this to be 1? Let me ask you this question in this way, yes?
The numerator and the denominator are the same.
And?
That means it's 1. You divide this.
No, and I want to respect the algebra of real numbers. Yes? Because in the algebra of real numbers, if I have a number divided by itself, it is 1. And I told you from the beginning that I want to keep the rules. This is 1. I would say it's good it to be 1. Okay? Okay, and then the numerators are multiplied because if I want to multiply two fractions in the set of real numbers, I know the rule. I multiply. So I want to respect that rule. Okay? And then I will continue my calculation. So let us do this in our head. Can you do that? Because A times C is just AC. What is the other real part that I will get? Do you agree with me? If I multiply this with that one, then it gives me an I squared. I squared is minus 1. So what will be the answer? So let me write it. BI multiplied by minus DI. It becomes minus BDI squared. But I squared is negative 1. That becomes BD. And BD, I put it next to this one. Yes, I wrote it correctly. You see this up there. And then the imaginary parts. I have to multiply BI by C, which gives me BCI. I put I outside. And then I multiply this by that. It gives me minus ADI. I put the I outside, so D is left. What for this one, of course, you can start multiplying, but there is a simpler way to do that, and I want you to learn to do that yourself. So what is this rule reminding you of? A number plus another number, the same number minus that number. The conjugate pattern. So this becomes the first one squared minus the second one squared. Yes? And then let me continue a little bit. So this becomes AC plus BD, and then I have BC minus AD, and then I have I divided by. So let us just do this in a scratch paper. So I have minus DI squared. But this becomes minus D squared I squared. Why? Because I told you I want to respect the algebra of real numbers. But what is I squared? Is minus 1. So this becomes plus D squared. Okay, and then it means that C squared is plus D squared. And what I do, I take this one divided by that, because still I want to respect the algebra of real numbers. And then I do the same thing here. And now you see that if I want to respect the rules of algebra in R, then this weird formula should work. So that is why we take this as the definition of division of two complex numbers. Yes? And then you know that this fraction, if you are working in real numbers, there is some limitation for b. What was that limitation? It cannot be 0. And that is the same thing here. Is it revealing itself? So if this w is 0, when this w becomes 0, can you tell me? We just learned that. If c plus di is equal to 0, this happens if and only if what? C and D are both equal to 0. So this means C is equal to D is equal to 0. Then if I ask you what is C squared plus D squared, what is your answer? 0, and then I have problems. So this is the same thing again. So it is automatically respected. I cannot divide two complex numbers unless the denominator is not 0. So you see that the rules are going very nicely. We are happy, yes? Okay, so there is only one thing we cannot divide, and that is the 0. We cannot divide by 0 again, and that's good. That's unfortunate. If we develop some algebra that we can divide by 0, that's also nice, yes? There is no way out of it, probably. Because the main problem in physics in this century is why quantum mechanics and general relativity are not consistent. When we want to merge them together, there are many things divided by 0 happening, yes. And then that's the only problem that we cannot solve it for the time being. Okay, and now let us do some example. So for example, I give you two numbers. Let us take the same two numbers. Okay, let me just make a mistake. So z is equal to 2 plus 3i, and let me write w is minus 1 minus 2i. If I ask you multiply z by w, you cannot memorize the formulas. They are not in the formula sheet, so you need to learn these tricks. You just multiply them. Multiplication is simple. So you write 2 plus 3i, you multiply it by 1 minus 2i, and then multiply. So what happens? 2 times minus 1 is minus 2, 2 times minus 2i is minus 4i, and then 3i times minus 1 is minus 3i, and then this becomes minus 6i squared. So what's the answer? Because I squared, you have to show this respect. Live with I, but don't live with higher powers of I. Okay, so I squared is negative 1, so this becomes positive 6. Positive 6 and negative 2 is positive 4. But minus 4i minus 3i is minus 7i. Simple as that. And let me divide. So let me divide z over w. So what can I do? I can write 2 plus 3i, and I can divide it by minus 1 minus 2i. By the way, there is a symbol for that. Let me just tell you. If a complex number is a plus bi, this z bar means the conjugate of that complex number. It means that I keep the real part the same. I change the sign of the imaginary part, from positive to negative or from negative to positive. For the time being, learn about this symbol, but I will discuss about this in more detail later. Okay, so you divide this and then you have to be patient, rewrite it again and multiply it by the conjugate of the denominator. So what is the conjugate of the denominator? I keep the real part the same. I change the sign of the imaginary part from positive to negative or from negative to positive. So this becomes plus 2i plus 2i. Yes? And then let us do the calculation. The calculation in the numerator is extremely simple. Just do it as usual. 2 times minus 1. 2 times 2i. 3i times minus 1. And 3i times 6i becomes, 3 times 2i becomes 6i squared. But even though you can still multiply, but I want you to learn to work with identities if possible. So that's a conjugate identity. So the answer becomes the first one squared minus the second one squared. Okay, and then let us do some simplifications. So can you help me for the numerator? What can I write?
Minus 4i plus I.
Not minus 4, minus 8. Because I squared is negative 1, so it becomes negative 6.
Yeah.
And then negative 2 is negative 8. And then 4i minus 3i is just positive I. But for the denominator, what happens? This becomes 1 squared, which is 1. Okay, can you tell me what should I write next? No, not 2.
No, plus 4.
Plus 4, not minus 4. Because it becomes 4i squared, but I squared is negative 1, so it will cancel that negative sign, so it becomes plus 4. Yes? And then if I ask you what can I write more, so it is not still a standard, it is 5, but you write it in a standard form by dividing minus 8 over 4 plus 1 over 5i. So for example, there are questions in the book, they give you two numbers. Instead of asking you to divide, they ask you what is the imaginary part of z over w. I have seen students take the imaginary part of that and then imaginary part of that and then divide. That's not correct. You have to do all the calculations, and at the very end, if I ask you what is the imaginary part of z over w, then you see it is 1 over 5. Is that clear? Yes or no? Okay. So let us continue a little bit. So what do you think? Is 1 over I a standard?
No.
No, because it seems to be a complex number, but it is not written in the standard form. Now we want to write it in the standard form. How should I do that? How can you imagine I? I is 0 plus 1i. Yes? But now can you tell me what is I bar?
0 plus
0 minus 1i. But a better name for 0 minus 1i is what?
minus I.
Minus I. So the conjugate of I is negative I. So if I insist you to do this, you rewrite the fraction. You're following the same rule. You multiply the numerator and the denominator by the conjugate of the denominator, which is minus I. Yes? And then what happens? 1 times minus I is minus I. I times minus I becomes minus I squared. But what is minus I squared? I squared itself is negative 1. So negative I squared is positive 1. And this is positive 1, so this becomes minus I divided by 1. It's minus I. Is it a standard? So can you answer this question? Instead of asking you the question in that way, if I ask you what is this, what is your answer? you have to still do the same thing and read the real part at the very end. So what is the real part?
0.
0. And what is the imaginary part?
Minus I.
Not minus I.
Minus 1.
Minus 1. Thank you. Okay. So that's also interesting, by the way. This does not happen in real numbers, yes? Can you imagine of a number whose reciprocal is negative of itself? So it was interesting. 1 over I turns out to be negative of I. There are no real numbers with that property that when I find 1 over it, it becomes negative of itself. But in the complex numbers, some weird things happen. As far as everything is consistent, we do not bother. Is that clear? Okay. The next step, what is coming next? We introduced the concept of complex numbers. We'll learn what is the meaning of them being equal. And then we'll learn how to add, subtract, multiply, and then divide. What's coming next? Lunch, maybe? Yes?
Powers.
Powers. Yes. So there are powers. So what is the meaning of powers? And then I told you that probably we want to keep the algebra, but fraction powers and other powers are so complicated in complex numbers, but we still can work like matrices, the people who have made. So we can talk about integer powers. So if I say, for example, z is a complex number, what do you think I will define z squared? I want to keep the algebra the same. So what's a good definition for z squared, even if z is a complex number, yes?
Probably a plus b in parentheses squared.
Not just z times itself. Yes, you are right, but z times z, yes, what you mean is this. Yes? If I ask you what is z cubed, what is the good definition for that? Z times z. Okay? So z to power n, if n is a natural number, is defined to be z multiplied by z up to zn times. Okay, but what do you expect I will define z to power 0? 1. I want to keep the algebra the same. And then what do you think I will define z to power minus n if n is an integer? If it's a natural number. Z to power minus 5. What do you think I will define it?
1 over z.
Yeah, exactly, yes, as before. Yes? So for example, can you tell me what is this number? Okay, so what is I to power 2? You already know. Let me ask you, what is I to power 3? Can I simplify it more? Yes?
You can rewrite it as I squared times
I, but I squared is
minus 1.
minus 1, so it becomes minus I. If I ask you what is I to the 4th, you can write it as I squared to the power of 2. Why I am allowed to use this rule? Because I told you I want to keep the algebra of R the same. So this becomes, instead of I squared, I put minus 1, but I have another squared there, so the answer is 1. So for example, what is I to the power of 243? What should I do with this? Yes?
You can see a pattern for that. If the power is even, the answer is minus 1.
No, that pattern is the naive pattern in the beginning. I want you to, that's not correct. Because 2 is even, the answer is minus 1, you are right. But I to the 4th, again 4 is even, but the answer is positive 1. Yes? So the pattern of evenness or oddness is not that good pattern. Okay. But you don't need to look at those patterns. What you have in your hand is I squared is minus 1. So try to write everything in terms of I squared. So what can I write? I can write I squared to the power of 121, but I need one extra I. Because if I multiply them, it becomes 242, and I need one more I. But this one is how much? How much, by the way, is not correct. I cannot say what is the value of a complex number.
It's minus 1.
Yes, it's minus 1 to the power of 121 times I. But what is this number?
Minus 1.
Minus 1, so the answer to this one is also minus 1. So can you calculate this one? I to the power of minus 13. What can I do with I to the power of minus 13? According to the definition, this is a negative integer. So what should I do? The last definition, yes? So I write it as 1 over I to the power of 13. And instead of I to power 13, what can I do? I can write I to power 2 to the power of 6 multiplied by next to I. Yes? And then what's the answer? It is 1 over minus 1 to power 6 times I. But this one is 1, it's 1 over I, but it's still not a standard, but we learn it's minus I. Yes? Of course, if I hadn't done this calculation before, so you have to solve, you have to add this solution to the rest of the problem and come with minus 1 as well. Yes?
It seems like a pattern that if the power ends with 3, it's minus I.
Yeah, the pattern is 4k plus r.
Okay.
So you need to, instead of saying that odd or even, you need to consider the remainder of the division of the power with respect to 4.
Okay.
So the remainder will be 0 according to number theory, 0, 1, 2, or 3. And according to which one of these remainders are then for you, then you can see the pattern. Yeah, if you want to play the game, that's a good game, but I myself prefer to use always I squared. I don't need to remember more things. Okay. By the way, let me give you another example. I can stop here. So, for example, I want to calculate this. One plus I to power 100. Or might be, let me ask the question this way. Let Z be this. Let Z be this. What is the imaginary part of Z? Yes? Of course, this problem in principle is not hard, but in practice it's extremely hard. Because if you want to answer this directly, by multiplying this by itself 100 times, it will work out, by the way. But there will be 2 to the power of 100 terms involved, which is a huge astronomical number. Okay? But is there another way to do it? This is engineered in a way that this can be done very quickly. If I change this number from 1 to 2, then this will not work. By the way, it will work later when we learn about Demoire's formula in complex numbers. But for the time being, what can I do with this? Yes?
I think you can write as 1 plus I squared like that to the 50.
To the 50. With the hope that 1 plus I squared is better. And that's the experience you got from matrix theory, yes? You remember we had something, if I want to calculate the high powers of matrix, it's always good to calculate the low powers sometimes. Okay, so let us just do that. So what is the answer? So what you propose, I will follow. By the way, this is a coincidence and it works. But sometimes you also need to solve problems case by case. You don't need to solve it in full generality. Okay, but what can I do with this one? Can I use identities in complex numbers? Yes, because I told you that I want to keep the algebra the same. So the first one squared, 2 times the first one times the second one squared. But why this is now helpful? Because coincidentally, I squared is minus 1, I can get rid of this positive 1. So what is left is 2i to the power of 50, and then this becomes 2 to the power of 50, I to the power of 50. For 2 to the power 50, I will not do anything. It's big enough. But I to the power 50, I learned what to do today. Now, what can I do for I to the power of 50?
I squared.
So I to the power of 50, so let me write all of it. So it becomes 2 to the power 50. Instead of I to the power 50, I write I to the power of 2 to the power of 25. But 2 to the power 50 is the same. I to the power of 2 is minus 1 to the power 25. But minus 1 to the power 25, 25 is odd, it becomes minus, and then I get that. Okay, so what is the imaginary part? Yes, imaginary part of z is 0. If I had asked you what is the real part, what's the answer? Minus 2 to the power of 50. Yes? Okay, one more thing, and we are done. Of course, you already know that, but let me also solve that one. This is the last problem for today. So solve z squared plus 2z plus 10 equals to 0 in complex numbers. So this is why this is a new lesson for you. Of course, solving this, you can use PQ or ABC formula. But if I want, let me use ABC formula. If I want to solve that one, what do I write? I write minus b plus or minus square root of b squared minus 4 times a times c. And then divided by 2 times a. So in Math 2C, if you wanted to solve a quadratic equation, for example, either you use ABC or PQ formula, I've used ABC formula here, then you realize that you are in trouble. Why? Because this becomes minus 2 plus or minus which number? Square root of which number? Minus 36. This is positive 4 minus 40. And that is why in Math 2C, that was the end of the problem. What do you say if it were Math 2C problem? No real solutions. And that's why we actually use the adjective real solutions, because there is another solution to that, and that's the complex numbers. So what do you do here? You can imagine that the square root of minus 36 is the square root of 36 times minus 1, and I want to keep the algebra the same, so I just write it as like this. But the square root of 36 is 6, square root of minus 1 is I. Don't keep it like this. You don't need to do it, you can do it in your head. So the answer to this part is 6i, there is a plus and minus. So it's minus 2 plus or minus 6i divided by 2. I factor a 2 out, it becomes minus 1 plus or minus 3i divided by 2. 2 and 2 are gone, so the answer becomes this. So there are 2 solutions, but none of these solutions are real. Yes? What does it mean? It means that if you draw the graph of this function, which is a parabola, do you expect to see these on the real axis? No, there are no intersections. The roots are not real, that you can see them on the real line. Yes? So, yeah, this parabola would pass something like this, where this point is 10. Okay, so you see that there are no intersections. If you get this impression that, okay, there are no intersections, there are no zeros, yes, you're right, in some sense, there are no real zeros, but there are complex zeros. So that you have respect. Okay, is that understandable? Okay. By the way, I skipped one part of the previous chapter. I will come back to that, which is not, of course, in the exam. Okay? Thank you very much.